lecture, and it is good that it is the last for me because I'm almost falling asleep now. I worked hard yesterday to prepare my lecture for the morning, but preparing this lecture, I did it during your talk, Jennifer. So, let's see. Let us see how it goes. So, there is one little thing that I want to still say about what I said this morning. So there is this ZP to the R, and then we have this kappa map to the ZP points of T with the residue disk of the little t, and we have this U, the p-adic points of the curve at the residue disk at the little u that goes there with the JB tilde map, and we want to intersect this. So maybe I should say there is a question, and this is a question that maybe somebody can help me with. So how can we prove that, and I would say without doing computations, that the kappa of ZP to the R intersected with U ZP little u is finite. And of course, we always assume that R is at most G plus rho minus 2, right? That we always suppose. And this is a bit a silly question, because the people Jennifer and the other people that wrote this paper on the cursed curve, and they can do it, right? I think if R is less than that, they have a proof that it is finite. But how can you do it without doing the whole translation of the geometric approach to their approach? Is there a way to do it? And what can you use, right? Of course, this must follow. This should follow from our choice of these, say, these line bundles L1 up to L rho minus 1, right, on J, that were trivial on the curve, and that from our choice, namely, that they are Z-linearly independent, even in the Néron-Severi group of the generic fiber of our Jacobian, right? So we chose them like that. They were selected to be trivial on C, but if you remember well, this kernel in the map from the Picard group of the Jacobian to the Picard group of the curve came from the Néron-Severi group. So they are not just a little bit non-trivial, no, they are really non-trivial. So that is, if somebody can help me with that, or can just publish it, I would be very grateful. And then another thing is that this kappa map here has so here is one little thing, here is a second little thing. This kappa, by reduction, gives a map from the R-dimensional affine space over Fp to this tangent space. The tangent space, now, this is the T for tangent space, this is the T for the object we made, right? And we take its fiber over Fp, and we take the tangent space at the point T, right? So we have this kappa bar map, if you remember well. This, so this, I don't think I said that this morning. This can be non-injective. I mean, I haven't seen it happen, but I'm sure it can happen. So, for example, I will give you an example when this will happen. If rho is equal to 1, then J and T are the same thing. And if this, and suppose that it could happen that you take your model Y group and you take the kernel of reduction at the prime P, and if this would be equal to the kernel of J of Z to J of Z mod P squared Z, then my whole thing, then this kappa bar is actually 0. Then kappa bar is 0, because the things are 0 mod P squared, where I only ask them to be trivial in J of Fp. So they are, if I then look at the level of tangent spaces, I get 0. So if this would happen by some coincidence, right, and that would be very coincidental, because then really if you change the prime, it will disappear after some time, it cannot always happen, then this is a situation where going to the next prime will just solve your troubles, okay, and I wanted to mention that, that's all. So let's go to the real topic of these 50 minutes. So I have two aims. So the first is show that the A bar that we saw this morning, that was a FP algebra obtained by quotienting the polynomial algebra in variables Z1 up to ZR by the kappa upper star of the Fj bars, right? It's a thing that this thing, as in theorem 4.12, by the way, this is 1, can really be computed if you have an explicit curve and explicit generators for the model Y group. You should have everything to do this. That is, make it and everything that you have to, that you need to get it explicit, right? So that it is ready for input in the computer, right? That is what you would like, and I want to show you or to convince you that we can do this. And well, there is of course the example at the end of the, in section 8 of the paper where Guido, where is Guido? He went a few rows back. Where he worked out one case, and you can look up there how it works in all detail, right? But maybe in my 50 minutes I do something not as detailed as that. And the second thing is show that the computations that you have to do and so are not so bad, right? And this makes us almost return to the issue of the Jacobian. Okay, good. So that is what I would like to do. This point 1, that is about sections 6 and 7 of the preprint. And let's start. We are going to do 6. So this is about. So who was the main actor here in this whole issue of mine, this approach, or of us? It is the Poincaré torsor, right? The Poincaré torsor plays the main role, and we want to. It's a line bundle on the Jacobian times the Jacobian. So to understand it, you have to, well, first of all, understand the Jacobian, and then some line bundle on it. That is so that is the point. Now, as a guiding principle, before we start even doing this, I would say. Eventually, everything comes down to line bundles on the curve, because the Jacobian is the moduli space for line bundles on the curve that are fiberwise of degree 0. So we will have to deal with line bundles on the curve, and if you do that, rigidify them, by all means. At the base point B. That is why we have a base point. So if you, I don't think I talked about that really up to now. If I have a curve over a scheme S, and you can think of, for example, the S to correspond to Z1 over NZ, then I have a smooth curve and here is the C that we want to look at. Let us look at that. The Picard scheme of that. If I take an S is then, yeah, something like this. I take T, not the T that I am talking about all the time, but a test scheme, just any S scheme. If I take the T points of that, then in the situation we have, that it is this. It is the Picard group of C pulled back to T, divided out by the image of the Picard group of T. This is the, well, it is the relative Picard functor. The definition is that you should look at this thing here and then sheafify it for some fancy topology on spec S or so, or on S. But if you have a base point, then you don't need to do that. This is a good definition, but this is not a very convenient way to work with it. Much better is to say that this is also the set of pairs L, phi, where L is an invertible O module on C base change to T, and phi is the rigidification at the point B, so that means O of T isomorphism to B upper star, maybe B base change to T upper star of L. Okay, you look at these things and you look at that up to isomorphism. Now this doesn't look for necessarily better than the other one, but the good message is that such objects have no non-trivial automorphisms. So that means they are rigid. And that means if you have a moduli space that classifies them up to isomorphism, you also have a universal object. And it's easy to work with that. So that is a good advice, I think, for everybody to apply this. And then let me say what you can find in this section 6 of our preprint. So there is a proposition numbered 6.3.2. This section 6 is actually very long, but it's also self-contained, I think. So that is good, and it does the whole job. It starts with treating the case of smooth, proper curves over base schemes, arbitrary base schemes, because that doesn't cost anything more. And then it looks at how it extends to this proper regular model that we have, and how to work with the Néron model of the Jacobian and the extension of the Poincaré torsor on that. And that is all. The last things that I just said are very technical, and I advise you to only look at that if you need it. Right? First, look at the nice case of a proper smooth curve. So here, S is any scheme that is quite general. C to S is a proper smooth curve. B, say, of genus G greater or equal 1. B is a section, an S point. D is a number greater or equal than 0. And then there exist unique morphisms of GM torsors rigidified, well, compatible, let's say, with rigidifications. And where are they? Well, I have to draw quite a... So here is C times Sj. So here I have the product of the curve and its Jacobian, and over it, because I rigidify things, I have a universal object, and this is called L univ torsor, right? I said I take the universal line bundle on the curve with parameter space a Jacobian, and I remove the 0 section so that I have this torsor. Okay, the next thing is I have J times S J dual, And I have a map here that sends, well, this is the embedding times the inverse of the pullback map, right? We discussed these things before. And here I have the Poincaré torsor, and I say, okay, this is already one nice message, that if you pull back the Poincaré torsor in this way, you get the universal line bundle on the curve times the Jacobian. Okay? And rigidification, so this one is rigidified at the point B of the curve, and also actually at the zero of the Jacobian. And this is rigidified at J times 0 and 0 times J dual. These things have nice rigidifications. We don't like the dual of the Jacobian so much, so we translate it to the Jacobian itself. We have this map, and it was almost up to an inverse and assign the principal polarization, so we do what everybody does. If you have a Jacobian, you don't need to talk about the dual, you can talk about the Jacobian itself, right? And then, just for the sake of notation, I think we call this M cross, okay? And this is more a definition, right? This is not a theorem or a proposition. This is the definition of M cross. And then we have something that is helping better, J times S C D, okay? And we have here something that I will have to explain, but this is a step to make the thing really more explicit. So this is the D fiber product power of C, so it is C times C times C, D times, over the base scheme S, modulo the action of the symmetric group on D elements. And this is the moduli space of effective divisors of degree D on C over S. Okay? So this is a first step to and here, let's say it is identity comma sum, or times the sum map, right? You have to sum the, well, actually it's a point of C to the D with the parenthesis is an unordered set of D points on the curve. Well, and then you add them as divisor, and that gives you this map. Okay, so then what is this thing here, right? So let me write that as a with this ND. Now the line bundle, or the torsor, what we want. Okay, it is the norm, and I will have to explain a little over the universal divisor base change to J. I will explain a bit more over J times S C to the D of the L univ base changed to C to the D. So this, let me draw the picture. I have C times C to the D mapping with projection to the D symmetric product, and because of the moduli space interpretation of this symmetric power, we have inside there the relative divisor, the univ, right? We have that is the universal divisor of degree D on C, effective divisor, and this map here is a finite locally free of degree D, and if you have a finite locally free map of schemes and you have a line bundle on the source, you can take its norm to the base. So what you do is, on an open affine of the base, you get its inverse image is affine. You have a ring, you have here a ring A, there a ring B that is locally free of rank D as an A module. You have a locally free module of rank 1 over it. Then you say, I do the norm. Okay, and we will see a bit later what that means if everything is given by points. Okay, so we also have, say, C, so we want to have, so here is on C times C to the D, there we have this divisor. And I think over C times Sj we have the universal line bundle. And I want a situation where I have both, so that I can take the norm of the line bundle, so I can restrict the line bundle to the divisor and then take the norm. Right? That is what I want to do. So on which space do I have that? Well, I need C and C to the D, but also J. So I'm going to do that on C times Sj times Sc to the D. Right? On this I have L univ base changed to C to the D, and I have in it D base changed by J, right? And then I can get rid of the C by taking the norm. So here I can take the norm. Now this formula makes sense, right? I can restrict this line bundle to this D universal base change today here, and then norm over this finite locally free map of degree D. That is the recipe to do this, and I'll give you an example of how this works out so that you can see. And this is written out in some formula 6.3.12 in the preprint. If you do this M that I just had here, right? This M is the Poincaré bundle, but only transformed to live on J times J. There is an S missing there. We would like to describe that, and then you could say, well, here I have sum over some finite set I, xi minus yi, and the other coordinate is the degree 0 divisor, also a difference of points, uj minus vj, like that. If I would like to know this, what does my previous formula say? It says, oh yeah, let's say that all these xi, yi, and uj and vj are S sections of C over S, okay? They are S points of C. So for S you could take Q or you could take FP or anything you like. This is canonically the same as the tensor product over all the J's of, I have to take this, the line bundle attached to this divisor and pull it back by these sections. Then I get something on S, and I'm going to tensor everything. So I do uj upper star of O of C over S. So this is the structure sheaf of C. Well, let's just say OC. I get here the divisor. I leave it as it is. xi minus yi. Okay, this is on the curve, the line bundle attached to a divisor. I pull it back with the section uj, and I should also do it with the vj, but then with a sign. So let me say tensor over os with vj upper star of oc. And now I take the sum of yi minus xi. Okay? And I hope, and in the tensor product, you have to do the whole thing. Okay? Yeah? That's what it is, and it really makes sense. You would say, well, if I work over a field, what do I get? I get a one-dimensional vector space, okay. But still, you can do things with one-dimensional vector spaces, even if they're all isomorphic. As long as you have canonical isomorphisms between them, it means something, okay. So this is how to make this Poincaré torsor explicit. This is how it works, okay? Okay, then we stop with that. How much time do I still have? 25 minutes, right? So then a few words about paragraph 7. So here What is still missing from making everything explicit? That is that to make these line bundles Li on J, that are trivial when you restrict them to C, we used endomorphisms or morphisms from J to J dual. And so that looks a bit terrifying too, because how do you describe that if you do not want to describe J as a scheme? Right? You want to make that easier. So let's say that we pick one of these things. Alpha will be, so they were of the form translation by a point Bi preceded by some Fi, right? And this F, and now I will not make any longer a difference between J and J dual. Let's say that this was a morphism of schemes over Q from J to itself, okay? That is what I want to so make this explicit. And so also this, we have to get rid of the Jacobian. Huh? You hear me say it? We want to have a way to describe this without the Jacobian. Okay. So again, I give you a nice diagram. Here we start with the curve C over Q. We put it by the diagonal map in CQ, well, say C times C over Q. This we can put in the Jacobian over Q with the JB. This we can put with identity comma this alpha that we have there to J times J over Q. And I want first to have a nice commutative diagram here. We can look at the curve times the Jacobian over Q. And we can also look at the same thing again, curve times Jacobian over Q. And there are arrows all the way like this. I want that this commutes, so I do the diagonal. Then I do the identity times the embedding of the curve in the Jacobian. That's the only thing you can do here. Then we still have to do identity on the curve. And now we can do this alpha. And here we do the curve. We finally embed the first factor and we do the identity on the J. Okay, then you can check that this is a trivially commuting diagram. Here we have, say, we look at this Poincaré torsor, but then on J times J. And by definition, what we had to do, we had to pull this back, and we should call this T alpha. Okay? And we wanted that this is trivial on CQ, right? That is what we want. And now I tell you what happens if you pull this back by this stuff. So here you get L universal cross. Okay? That is the pullback of this GM torsor to C times J. And then when you pull it back here, we will just give it a name, L alpha cross, right? Okay? So then you see that here we have this T alpha, and JB upper star T alpha is trivial on C over Q is equivalent to this L alpha be trivial on the diagonal in C times C over Q, right? It ends up here. I can pull it back from here to here, or this one from there to there. And it works also the other way around. If I start with a line bundle here on C times C over Q, that is of degree 0 on fibers for both projections and rigidified in the first factor at the point B, then this will give me what I need, namely a map from the Jacobian to the Jacobian. You get that by, so how do I explain that? If you have a line bundle of fiber-wise degree 0 here and rigidified at B, there is a unique map from C to J, and that is the alpha composed with the JB here, that makes it the pullback of the universal one. There is a map from C to J, and that is not just the embedding, there is this alpha then. And you can extend it to C times J to here by Albanese functoriality. You can say, well, the Jacobian, every point in the Jacobian is a sum of points of the curve. And if you know what the map from the curve to the Jacobian is supposed to do, you can extend it linearly to the Jacobian. So you can start with a line bundle here, and the only condition is that it should be trivial on the diagonal, then you get exactly such an endomorphism of the Jacobian as we wanted. So we have described it without doing geometry on the Jacobian. Okay, and that was what is necessary to solve these problems. Okay, so then finally the computations, right? So I hope that I have somehow made it plausible that all these things that we need are explicit enough to put in a computer. Now the computer has to calculate with it. And so what does that look like, right? So computations. In the Z mod P squared, I also wanted, I said that already a few times. So in the T or in the J, it is enough to do most of the computations with points with values in Z mod P or Z mod P squared. Huh? So let me also say J of Fp and T of Fp. Those things are enough for us. So first of all, if you want to do computations in the Jacobian, J of Fp, what are you doing? You do line bundles up to isomorphism on C over Z mod P squared Z or C over Fp. Right? So actually, that is clear that you don't need the geometry of the Jacobian, right? You just need to handle line bundles on the curve. And not even the curve over some difficult base, but over some very small base like Fp or Z mod P squared. So that, and how do you do that? Well, you can work with divisors. Huh? So, for example, e.g. work with divisors. And maybe I'll say a little bit about it in a moment. And the second thing is, if you want to lift this to computations on this torsor, actually, this is no extra effort. If you use rigidified line bundles, because then here you would work up to isomorphism, but there is each time a unique isomorphism, so you can keep track of points on the line bundles all the time. And that means that you are actually doing computations on T. So that is not an extra, no extra work. So that is the thing that I want to say. So then finally, we are getting back to so finally, how do you do the computations in the Jacobian? Finally, we get back to the Jacobian. Is it good or is it bad, right? That is the question. Is a Jacobian something good or bad? And let me compare it with, before we discuss the case of the Jacobian, let us look at another suspect. Who is the other suspect? So that is something that we are usually not afraid of. So that is why when I try to show that the Jacobian is not bad, I give you somebody else who is not bad, but he still looks a bit like the Jacobian in a certain sense. Huh? So we compare with the Grassmannian, right? And so let's say the Grassmannian, to have any relation with the Jacobian, let's say that it is classifying G-dimensional spaces in a 2G-dimensional space, right? So this is the Grassmannian. I always forget how many N's and S's, so let me put enough of them, right? Grassmannian of G-dimensional subspaces in a 2G-dimensional space. So the dimension of this, right? I want to know the dimension. And for that, I say, well, you take the GL2 of dimension 2G by 2G divided by the stabilizer of one of such. That's this. And what is left, that is this little square here. So the dimension is G squared, I think. Okay? Dick agrees with this. He says this. Good. And so now, where do you embed it in, right? So we are not afraid of it. It is even of higher dimension than the Jacobian. The Jacobian is only G-dimensional. This is the square. Embedding. Embedded. If you would like to study this as a variety, and if you are a bit naive, you think, okay, I have to embed it in a projective space. So in which projective space do you embed this? I think that a guy called Plucker had a solution to that, and it means that you do this binomial coefficient -1, I think. Right? Because you look at the exterior algebra, or the G exterior power of the vector space of dimension 2G, and you can embed your Grassmannian in there. Now I will, binomial coefficients are big, especially the middle one. It is bigger than all the others. So this is bigger than 2 to the 2G divided by 2G plus 1. Yeah? So this grows as hard as the space in which you embed a genus G, the Jacobian of a G-dimensional abelian variety, just as bad. Is anybody here afraid of doing computations in the Grassmannian? No. So that makes my point. So this is not a problem. Not a problem. And why is it not a problem? Just describe subspaces in terms by giving a basis, right? That is not a big thing, not a big deal. Every student after a first-year linear algebra course is supposed to be able to do this. So then we say, okay, so now how does this compare to the Jacobian? So let me say that. I will say the Jacobian's case, now J, right? Okay, it is, criminals are not named by their full name. It is J. J. The other one was Gr. So, yeah, I say it's just the same. And why is it just the same? We fix a line bundle L on C, and now I leave it a bit ambiguous over which base this C is. You can think over Q or over Z mod P squared. We fix an L on C of degree, say, greater or equal than 3G minus 1. So this is not so small, but also not extremely big. Then for every D greater or equal 0 effective divisor, well, it is effective divisor of degree G. You know, everybody who works with Jacobians knows that degree G is sufficient to work with it. You have this map. You have H0 on C of L minus D. This goes injectively into H0 on C of L. Now this is a fixed vector space, and this is a codimension G subspace, right? Because the H1 of this thing is 0 because the degree is 2G minus 1, which is just 1 bigger than 2G minus 2. So by the Serre duality, the H1 vanishes, and you know that this is exactly the right codimension, right? And now, if you are not afraid of the Grassmannian, then I have convinced you that this is a good way to encode your divisors, because you have just to do a codimension G subspace in something. Well, I let you compute the dimension there, but it is not a big deal. And if you want to see details of this, of how you do this, you should see work of Kamal Khoury-Makdisi. Mark Deasy or Peter Bruin in his thesis, or actually with implementations by Nicolas Mascot, who used this already since some time. So that, I think, is the very end of my course, yeah. So, and it is time. No, it is time for questions, right? Are there questions? So we have. So as the previous speakers, I finish a bit early. I think at the end of a long day, nobody complains. Could you speak through the microphone?
So my question is, have you exonerated the Jacobians?
Well, I am just a lawyer, you see. So I think the jury has to decide. Huh? Is it, so somebody wants to, is there a chairman for the jury? Do you call it like that?
Maybe some deliberation is
But
required.
I tried. You see, well, maybe this is the first time I act as a lawyer. I'm not used to that. But I hope I convinced some people. Well, if there are no questions, then I would like actually, as the last speaker, to thank the organizers of this wonderful winter school. It was a big pleasure for me, and I had never seen this, but it went beyond my expectations. So let's give an applause for the organizers. Yeah. Especially in these times of Corona. Huh?
Well, let's thank Vas again for his wonderful lecture series.